So remember the web graphs that we discussed before? If you don't remember, let me revise it quickly for you all. A web graph is basically a graph with a node. Okay, this node represents let's say a page like this, a page pointing to another page, right? So here is a page which has a hyperlink to another page. You click on this, you are taken to a new page, right? And internet has millions and millions of such pages, right? Several such pages, a whole lot of such pages, correct? And then I look at the underlying graph, and that's called the web graph, the graph of the World Wide Web. So I'm going to consider that right now. Okay, so typically a node represents a page. This represents a page, and an incoming link to it represents a link that is pointing to this page. As simple as that, right? Okay. So there may be many such incoming links to a web page from some other page. By that I mean, if I put a link to your home page from my home page, then I put an edge from my home page to your home page. Home pages are all nodes here, and if there's a link from one page to the other, you put a directed edge, right? These are all the web pages from where there is a link put to this page. Okay. So these are the incoming links to a given node, right? Here the incoming link is, incoming degree is 3, right? That's called the degree. Now, let me plot on x and y axis the following. On x axis, I will write the incoming degree. And on y axis, I will draw the distribution, right? And I'll observe what's happening here. I observe that there is a drop like this. Unlike the previous case, we don't see a normal distribution here. Okay? And in fact, a closer observation even tells me that this plot very much resembles 1 over k square, where k is this, k is the x-axis. It resembles this, right? And this is called the power law. Right, the law where the law which states that some distributions do not exhibit normal behavior. You don't see a bell curve there. You see a drop like this, Okay? Okay. So the exponent here is 2. It can be anything for what we know. It can be anything. But in this case, in the case of the web links, it turns out to be k square. Okay. So what have we observed so far? When you plotted the incoming degree versus the distribution, right, you got this for web graphs. But then when this was 1 over k square, but then there's a difference. What's the difference? Normal versus power law. What is the difference? See, initially you saw we plotted 2 graphs. One was normal, one was power law, right? What is the huge difference between these 2 things? What does power law tell us? Okay, which normal distribution didn't? Do you see this? In fact, this actually extends. Right? Do you see the yellow line here? Let me show that to you once again. This actually extends. It goes beyond. For a long time, you will see a curve like this. Okay? So let me just extend this green line also. And what does this signify? What is this band here? What is this band here? What does it denote? Please look at the x and y axis. It's rather self-explanatory. What does it denote? It denotes something very significant. Observe carefully. It denotes that this continues. This goes on. Goes on means what? It means there are nodes with very high incoming degree. Do you think that's what this means? Look at this this side, this x-axis. X-axis means what? We just wrote it. The incoming degree. The incoming degree is very high here as it goes on the right side of the x-axis. And the yellow line denotes that there are nodes with very, very high degree. That was not the case in normal distribution, as you remember, correct? The power law simply says that the curve extends beyond a stage, and it sort of is close to the x-axis, although it doesn't become equal to x-axis. It goes on, which means it shows us of the existence of nodes that have very high incoming degree, right? Fine. Here's the question. Why do you observe this drop of the curve? And secondly, how come there are so many nodes with higher and higher degrees observed in real world networks? I hope you remember that in the previous lecture, one of the previous two lectures, we observed that if you plot it for, let's say, a random graph, which is a GNP model with some 1000 nodes and probability 0.1, you observed that it was a quick drop. How was the graph? Remember, the graph was something like this, that's all. After this, there was no extension. Before this, there is no value, no node which satisfies this. It all lies between this and this. But in case of real world networks, we see that it sort of extends. Firstly, it drops and extends, right? Both funny and strange. Why is this happening will be the crux of this chapter and the crux of discussions in the forthcoming lectures. Okay, let's go ahead. Okay, so it has very high degrees what we observed. Remember that there are many nodes with very high degree. It goes on and on. This is called the power law. Okay. Power law is basically the drop of the plot. The distribution drops, okay, and that resembles a 1 over k to the 2 or k to the 3, or in general 1 over k to the alpha, let's say. Okay. All right. So the power law is a drop. It is observed in many situations, not just in what did we observe in the previous case? We saw the distribution of, let's say, the incoming nodes of a web graph, and we observed it's a power law. The immediate next question you may want to ask is, where exactly do I see power law apart from these web graphs? In fact, you see them in many situations. You will see them in telephonic conversations. Let me go back so that I can show them to you one by one. So you will actually see this distribution. This kind of distribution is observed in the telephonic conversation. For example, what does this mean? This means you again plot x and y axis. Okay. On x axis you plot the time duration of phone calls, and on y-axis you plot the number of such phone calls or percentage of such phone calls. Okay, both are one and the same, and you will observe that it's again a drop like this. Okay, so what do I mean by this? How many phone calls have been of 5-minute duration? A whole lot of them. How many of them have been of 10-minute duration? A whole lot, but relatively less compared to what used to happen for a 5-minute phone call duration. That's a whole lot. As you can see, 10 minutes is less, 15 minutes is a lot less, so on and so forth, right? And you do find this extends, and you do find there are phone calls which are of high time duration. Right? This distribution is also a power law, very surprisingly. Okay. Where else do we see power law? We see that in many places. In fact, these data sets are actually available online. You can just check. So where again do we see the distribution of song downloads? Right? What are the number of songs? What are those songs which are downloaded more than 10,000 times from a website? There are some official song download websites, right? So if you go and look at this, even this shows a power law. Okay, this shows a exponential drop like this. Okay, so which means power law is observed in many places. While we think it should have been a bell curve, in place of bell curve, there is a drop like this. Okay. So on. So there are many such networks. You can take a look at it. In fact, there are hundreds known till date, or maybe even more, right? I know at least a couple of dozens of very well-known networks that exhibit power law. And people have even looked at why exactly they exhibit power law, which will be the focus of our next lecture. So now we observed that there is a normal distribution. there's a power law distribution, right? So this we completely understood, right? We understood it completely. Why was it? I remember I took random variables and I showed you that the sum of random variables is what results in a curve like this, right? There's nothing much to explain there. And physicists, chemists, biologists, you name it, people have observed this normal distribution extensively. In statistics, this makes the crux of many observations, and they analyze it as well very nicely and neatly, and the math of it is completely understood, and it's also very nice and elegant. You may want to look at it in case you're interested. Okay, and what we need to understand is, we understood this, what we need to understand is this now, right? How does this combine? Let us understand this now. So our main focus that's coming next is we'll look at this power law networks, which is the web graph, and we'll ask this question: how did this happen? Why did this come here? What exactly made this curve appear like this, while we were actually expecting, what were we expecting? We were expecting something like this, right? Something like this we were expecting. We ended up getting something like this. Okay, we'll see more of it in the next lecture.